The journal entry is E5 for you guys. Topic is circuit calculations. Now, what we're going to do is we're going to take a look at something called Ohm's law. Okay, and again, we've been building series circuits, we've been building parallel circuits, but now we're going to measure some things about those circuits. There's a lot we can do once we have a circuit built relating these things that you see up here. So let's go ahead and see if we can figure out what they are. In this formula that we have, which we're going to use for Ohm's law, we have V is equal to I times R. I'm just curious, if we're talking about electricity and we're talking about circuits, anybody think they know what any one of those letters may stand for? Last class, they all knew the answers. I couldn't figure out how, and then I figured it out very quickly. Give me one. What?
Volts.
Yeah, V is something called voltage. And voltage, well, comes from your battery, and it's the amount of energy that you have to move electrons through a circuit. Okay, so we'll say energy to move electrons. If you're comfortable just writing the letter E with a negative for electrons, that's fine, that's acceptable. I'm going to write out the word electrons just so it's clear. Voltage is the energy available to move electrons through a circuit. And the batteries that you have supply the voltage. In fact, you have a 9-volt battery. You have that much energy to be able to move electrons through your circuit. Now, these other ones are a little bit more difficult. So I'm just curious, does anybody know what I or R stands for when we're talking about electricity? The R sometimes kids will get. What?
Radioactive.
No, nice try though. The radiochemistry is something we are going to talk about a little bit, and if that's not like really off the mark. Okay. Curious what? Rate? No, there is a rate in there though. It's actually the I. It's kind of an interesting one. If you flip the sheet over and look at the high school computation side, there might be some clues in there or some things that could help you out a little bit on the back of that page. Oh, you already collected it? Oh, did they? Okay, no, that's absolutely fine. Yeah, what's going on? No, actually, I think that's pretty much what you just said. Oh, he's got, wait, now this is unfair because he still has a sheet.
Resistance.
You know what?
Resistance.
R is something called resistance. So every circuit that you build is going to have voltage, the energy available to move electrons, and it's going to have resistance. I'm going to go ahead and draw a really simple series circuit down here. You don't need to draw it yet. We might draw it at the end. There you go. There's a schematic of a simple series circuit. In fact, it's something that all of you could easily build right now at this point. Your voltage is your battery. That's what's supplying the energy to move the electrons. What in this circuit would slow down the electrons? What in this circuit do the electrons have to do or power as they travel through the circuit? I know it sounds weird, but we'll try it this way. What?
The light bulb.
The light bulb. So the light bulb is resistance. The light bulb is a force, or supplies a force, I should say, that slows electrons. So while the voltage is pushing the electrons through, things like the light bulb serve as resistors or resistance. It's a force that slows down electrons as we go. Okay? So voltage pushes, supplies the energy. Resistance slows it down. By the way, there's probably some resistance in the switch, and there's resistance in the wire itself. If we hook this same circuit up, but I put a 50-mile wire, imagine that. Imagine you have a 9-volt battery, and you take a wire, and you clip it on the battery, and then you unroll this huge spool of wire, and you walk all the way to Oswego and back, and then connect it. You're probably not going to light the light bulb on the other side of that huge circuit because there's too much resistance. So the wire itself can supply resistance, the switch will supply some resistance, but our main resistor is the actual force. Is the actual light bulb itself. All right, so what's the I? The I is really strange. Do you know what the I is? Just
I have a
curious.
question.
Okay, no, I'll get back. Let me get back to it one second. What's the I then?
Current.
I is the current. Now, that probably makes no sense to you. Why would you ever have I stand for current? That's one of those weird things that scientists do. Ms. Oakley was talking about in math class. We can't double use letters in formulas. The only reason why they're not using a C for current is because C is already used by other things, okay? Which makes it incredibly strange. In science, capital C is used by specific heat, which is a computation that you'll be doing in here. And lowercase c is actually in physics. Lowercase c is the speed of light, which I know sounds like a really weird one. So C is already taken, so we use an I to give us current. Now, current is a word you've probably heard of before. Where have you heard the word current? I'm just curious. It doesn't even need to be based on electricity. Where have you heard the word current? Where have you heard current?
Like, when you go to the beach, you see that the current's like getting high.
Yeah, you can go, like water has a current. You can go up to a stream and see the current in the water. How many of you have heard that before? Talking about water having a current in it? Great, that's awesome. Because electricity also has a current. Electrons also flow. So current is kind of like the rate of flow. Bless you. Of electrons. That becomes relatively easy to draw on here now. Voltage pushes the electrons, the energy available to move them. Resistance is the thing that slows down the electrons, the thing that's getting done in the circuit, place where energy is changing into like motion or light or heat or something like that. And current is the flow of electrons themselves. So if we draw an arrow like that, we could just put a nice little I next to it and call that the current. The flow of electrons is the current. So now we have a relationship between voltage, resistance, and current. And I wrote my I sideways, which makes it look like an H to make it even more confusing for you. Now, for us to be able to do these calculations, there are a couple things that you need to know, and those are the units. Then we can go ahead and try a calculation using the things that you have here. But I did ignore your question, so I'm going to go ahead and take it now. What's going on? Or do you know the units?
Oh, I was going to take a guess.
Okay, so go ahead. Give me a guess for a unit here.
Is it the joules or?
Oh, joules.
Yeah.
Anytime we're talking about energy themselves, we talk in terms of joules, or the ability to do work. When we use Ohm's laws, we have specific units that we're going to use for voltage, current, and resistance. Okay, but it's cool that you bring that up because it's definitely related. Okay, the one that everybody knows is the unit for voltage. That's the one that most kids are pretty good with. Unit for voltage, you know?
Volts.
It's volts, which makes sense. So I'm going to go ahead and write that in green. The unit that we're going to use for voltage is volts, which is a big old capital V. 9-volt battery, lots of energy to move electrons. Okay. If you go up to a power line might be carrying 10,000 volts, 100,000 volts. Lots of energy to move electrons. You lick a 9-volt battery, do not lick a electrical power line. Okay? It has more energy to move those electrons through. These are the ones that are strange. Doesn't matter which one we do next. Here, let's do resistance next. Resistance is my favorite because it reminds me of cowboy pants. I know, it sounds incredibly strange. Yeah, resistance, you know? It's ohms. It's named for the dude. So the unit that we actually use is ohms.
Like ohms.
Like ohms, like yoga ohms. Like if you're in a gang, ohms. Possibly. Listen, it's ohms. But my favorite part about it is not the fact that it sounds like yoga or like you're in a gang in California. My favorite thing about it is it reminds me of cowboy pants. And I will explain that right now. The reason why it reminds me of cowboy pants is because they can't use an O for ohms as a unit at the end of a number. Okay, just curious. Can you raise your hand and tell me why you can't use O for a unit at the end of a number? Why is that?
Because it looks like a 0.
It looks like a 0, so you don't write down your sheet. Oh, good, it's 1 O. And then somebody else will look at it and be like, what? Is that 10? Is that 1 ohm? So they actually use the letter omega. And for some reason, I always think of cowboy pants when I see omega. I don't know, I always imagine, howdy, y'all. So for me, they're always the cowboy pants.
Is that the sign?
That's a symbol right there. So again, we can just end volts with a V. When we write a number, we can just write ohms as cowboy pants. And then, or we should say an O or omega. And then finally, current. Current is another one you may have heard of before. I'm just curious, you know?
Appearance or...
Close. You're reading it off the sheet there. It's the amperes is what they call them, okay? Very rarely do people say the word ampere. They'll just call it amp. Sometimes they'll have just a capital A. I've seen that on meters also, like the meters that you have here. So, voltage, energy available to move electrons through a circuit. Resistance, the force that slows down electrons as they're going through. And current is the actual flow of the electrons themselves. We're now ready to do some calculations because we have our units, our definitions, and we have a simple formula. So let's go ahead and get it rolling.